before we get started. So those who are interested in signing up for either of the dinner or the excursion, so please do so by lunch today. So the sign-up sheets are here. Also, the reimbursement forms for Indian participants from outside of Bangalore, ISI forms, fill it there and give it to Yogesh. Okay, and yeah, one more thing. So every day at the end of the day, the talks are all already uploaded on YouTube. So if you want to just refresh or whatever, you can look at those. And
we've also been posting the slides on this.
Oh, yeah, that's true. Yeah, slides are also posted. I think there's a folder that's been created and the email has been sent. Right. Okay. And yeah, is there anything else? Can you hear us, Yannick?
Hi, good morning to you. Yeah. Can you hear me?
Yeah.
Okay. All right, should I continue?
Yeah, please get started. Yeah, so Yannick will continue with the Mahler's conjecture and Bourgain's conjecture. Thanks.
Okay, so good morning, everybody. Thanks for showing up for the second talk. I guess it says the first talk was not a complete failure, so I take that as a positive sign. So like yesterday, please feel free to interrupt me at any time. Happy to make interactions and pauses and learn some things from the audience. Just recap a little bit. So yesterday I was discussing the notion of the LP support function. It's here in this box, and the LP Mahler volume, denoted by NP, and when P is infinity, this thing becomes the supremum of x dot y, where x is in k, and so that becomes the classical support function. Okay, so h infinity is just hk, and m infinity is just mk, which is the Mahler volume up to this normalization of n factorial, which is convenient and natural. Associated to these duality notions, let me just focus a little bit here. So associated to these duality notions, there is actually a geometric object, which is the LP polar body, and it's defined like this, or you could, just define it as the body associated to this near norm or norm with quotes. Okay, so this is the definition we came up with, and it just circumvented the lack of homogeneity of the LP support function. Okay, so the point of that whole definition, in some sense, was to make contact with the theory that Nazarov and Vodsky developed something like 10 years ago on Bergman kernels of tube domains over convex bodies. Okay, and so what these definitions do, that they give a convex geometric meaning to the Bergman kernel of the tube domain. Okay, and so that Bergman kernel on the diagonal is precisely the ratio of the volumes. So in other words, if you just assume that your body is normalized to have volume 1, then the Bergman kernel is exactly captured by the volume of the L1 polar. Okay, and so that's kind of the motivation for this whole development or definitions, if you wish, call it, and it's just another bridge between convex and complex. Okay, and so in some sense, what we were doing yesterday was an application of convex to complex. Okay, and the reason I say that is because actually there are some conjectures about Bergman kernels of tube domains. So this is an active field of study, and for instance, Dvorsky about 10 years ago conjectured that if you look at this quantity, it will be minimized. If you look at this quantity for K symmetric, it will be minimized for the Q in any dimension. And no progress has been made on this conjecture for 10 years. So in some sense, one of our motivations was, okay, let's use tools from convexity to rephrase this complex problem as a convex problem and then maybe solve it. Okay, and so in fact, what we saw yesterday is that Dvorsky's conjecture amounts essentially to the L1 Mahler conjecture in that family of conjectures that we stated yesterday. So I have it here. Right. So these, if you just allow P to be infinity, you get Mahler's conjectures. If you allow P to be 1, then this is, I mean, the lower bound is what Dvorsky conjecture for Bergman kernels. So, so at least, you know, there are known methods in convexity, and for instance, in dimension 2, dimension 3, the Mahler conjecture is known, and so one can hope that these methods can be, you know, maybe replicated for the LP Mahler conjecture, and you know, at least prove some lower dimensional cases of Dvorsky conjecture. Okay, so I'll come back to that later. Okay, so today, so that's kind of a recap for yesterday, and so today I want to go in the other direction in some sense, at least philosophically. And what I mean is that let us see if complex analysis, complex geometry can give something to convex. Okay, so it usually goes in the other direction, but sometimes it goes in the complex gives to convex direction. It's rare, but it happens. And a beautiful example is Bernson's proof that proof of Kuperberg's result in some sense, but he showed that the Borgman-Millman inequality holds with the constant pi. Okay, and so that's the best known constant, and he does that using methods of contour integrals and complex variables. So I think if you are a graduate student and you want to read a really beautiful paper that is completely accessible, you know, once you know basic analysis, then I would suggest that paper by Bernson from a couple of years ago in Advances in Math. So so anyway, so the hope here was that maybe using the fact that LP Mahler volumes are coming from a complex kind of motivation, maybe some methods of complex geometry can be harnessed, and something can be said about problems in convexity. Okay, and so this is the motivation, or kind of the long prologue, and so the conjecture that I want to discuss today is mostly, not only, but mostly I want to discuss the Bourgain's conjectures. Okay, and so let me just recall the notation, because this was 24 hours ago. So right, so we have it here on the bottom. Okay, so so CK is defined in units of volume square, and it's, for those of you familiar, it's just equal to a certain power of the isotropic constant, but it's a negative power. So all the inequalities that are usually stated like inequalities from above, they become inequalities from below, and the symmetry with the Mahler conjecture becomes more apparent, right? So that was kind of the reason to use this notation. And so and the Borgen's conjecture in their strong form say that this functional is bounded below by its value on the cube. If you look at symmetric bodies, and bounded below by the normalized simplex if you look at all bodies. All right, so that's CK. It's essentially just the volume squared divided by determinant of the covariant matrix. Okay, very, very explicit. And Borgen's conjecture says that this should be bounded by some constant at the end. Okay, and nobody has been able to show that yet. It's a big important open problem, and it has many reformulations and implications and stronger conjectures that imply it and so forth. So I mentioned a bunch of references yesterday. I'm not at all an expert on that. But the point of today is really to say, well, there is a complex point of view on this Borgen conjecture, which I think is novel and interesting. Okay, and so even if it doesn't solve the problem, or maybe it even cannot solve the problem, who knows? But at least it's an idea, which I think is interesting. So this is joint work with Bo Bernson and Blasis Mastrantonis I mentioned yesterday. So we phrased this convexity condition, which is has a parameter in it. Okay, so this parameter b is some positive number that you can think of as fixed. And once you fix that number, you get this property. And for every value of b, it's a different property. Okay, so and so you look at this function, which is you construct using the LP support function. So this is just a multiple of that function, and here you have the log determinant of the Hessian of that function. You add these two together, and you know that HPK is a convex function. So you kind of expect that if you take B to be very, very, very large, this will always be true. Okay, and so as we'll see, it's really, the point is to really understand what is the minimal B for which this actually holds. And so in some sense, this reduces Borgen's problem to something about like this. And the advantage of this condition is that it can be phrased in terms of complex geometric notions. Okay, and so anyway, let's accept this condition for the time being as something just given, and we'll see later why it's actually natural geometrically. Okay, and so the theorem says that if this condition holds for a particular body K, right? So you're fixing a body K, then you get an interesting relation between the C functional and the M functional. Okay, and so actually you get that the C functional is bounded below by the M functional, the sort of MP functionals, and the P here exactly depends on what B you can take here. Okay, so and then there is some dependence here as well. So in some sense, like I said, for B, essentially infinity, we know this is going to hold, but then here you don't really get anything. So you want this to hold for some small enough B, okay? And if you use some properties of LP Mahler volumes, you can get the kind of weaker result, which is but more convenient to use, which is just that C is just bounded below by the Mahler volume up to some power of B. Okay? And so what this observation shows is that if you happen to know that this, let me erase this a little bit. If you happen to know that this strange property star B holds for bodies in any dimension with B independent of dimension, okay, then here you get some constant independent of dimension, and hence you have solved the Bourgain conjecture, right? Because here you just want to bound this by a constant to the power n. So that's the punchline of this condition. Okay. So
This thing about the constant and Bourgain's conjecture, any prediction or on optimality?
what the constant should be?
Yeah.
Yeah, so this is in the first slide here. In the symmetric case, the constant should be 12. And in the non-symmetric case, it should be basically this, which is basically like e squared. So here it's 12, here it's basically e squared. Okay? All right. So, okay. But anyway, this estimate here, it doesn't even hope to give the best constant. It just, I mean, that's the strong, the exact constant is the strong version of Bourgain, and that's extremely, how to say, ambitious. Even Bourgain's conjecture is, you know, a field Mendel type problem. So here, this is just would give you some constant. It would give you the Bourgain conjecture, not the strong one. Okay, so let's delve into this condition a little bit and see how it relates to Bergman kernels. Okay, and so okay, and you know, just before doing that, I guess it makes sense to check that this condition B is holds for some B which is finite. Okay, so this is one of our main results, that actually star n plus 1 always holds. Okay, so this is not quite what would give the conjecture, right? Because the conjecture would need that this B does not depend on n, but the best we know right now is n plus 1. Okay, and so if you combine that with the previous theorem, right? So if you combine that with this theorem here, if you can put B to be linear in n, then you get the estimate that C of k is bigger than C times linear to the power n. So this is kind of ancient history and convexity theory and the history of Bourgain's conjecture. So this is essentially one of the first results that was ever proved, and it's considered easy today. It's like very easy result. So this is not sort of a real contribution to the advancement of our knowledge on Bourgain's conjecture in some sense, but we still think that conceptually it's interesting, and maybe it can be improved. So I'll talk about that. Okay, so like I said, this is known in the symmetric case by Milman-Pajor and by Dar, who improved that to all bodies. So this sort of gives a complex proof of something in convexity. And again, I'm sort of repeating this many times, but the idea is we've given something to Bergman kernels using convexity. Now we want to give back to convexity using Bergman kernels. Okay, and so I claim that this whole discussion with this star B and so forth is actually related to Bergman kernels. Okay, so that's what I want to discuss now. Okay, so Okay, so theorem three, okay, theorem three, I don't have a board, so I have to kind of keep going back and forth. But theorem three is that this star condition holds with B equals dimension plus one. Okay, and this star B again is this condition here. So I also sent the organizers the slides, so maybe you can even look at these slides at the same time. So anyway, all right. So we want to show this, and we have two proofs of that. Okay, so one is complex and one is convex. Okay, in the spirit of these lectures. So so for the complex proof, I need to introduce Bergman kernels, which are a little bit more advanced, let's say, than the Bergman kernels we looked at yesterday. So yesterday we really just looked at a domain and we looked at all L2 holomorphic functions, and that was the Bergman space. Okay, but you can look at kind of more sophisticated Bergman spaces, which are not necessarily associated to a domain and all the L2 holomorphic functions on the domain with respect to the Lebesgue measure. Okay, and so this is also a Bergman space here. So we take mu to be any probability measure on K, kind of supported really on K, not on a smaller linear subspace. So for instance, this mu could be the uniform measure on K. That would be kind of the classical choice. And another choice would be if K is a polytope, you could take mu to be the empirical measure supported on the vertices of the polytope. So that would work too. And really anything in between. So okay, and there is motivation for doing either one of these choices actually that comes from complex geometry. But at any rate, so what is this Bergman space? This is, for those familiar, this is a Paley-Wiener type space. And it's, you know, the word Paley-Wiener also appeared in Nazarov's work. And in fact, these kind of spaces are the kind of spaces that go into proving the formula for the Bergman kernel of tube domains. So it's kind of all in the same circle of ideas in some sense. Okay, and so we look at L2 holomorphic functions that are cooked up in this kind of Fourier type construction. You integrate an L2 function which is defined on K, which is defined on, I mean, okay, if you take mu to be what I said before, yeah, you can think of it as supported on K, but you know, more generally, it can be here you integrate over Rn, and you kind of average these Fourier modes or these kind of exponentials based on the weights of this original function here. Yeah. Okay, and then the inner product is defined just downstairs, if you wish. So this in some sense is very reminiscent of tube domains. You have a function downstairs and you construct a function upstairs. And you define the L2 inner product or the Hilbert space structure to be just the Hilbert space structure downstairs. Okay, so okay, and so and then the Bergman kernel here I don't I mean off the top of my head I don't have a formula for it. I'll have in a second, but then I want to find the formula for it, so I use the supremum characterization of the Bergman kernel. So this is something I mentioned yesterday, but I didn't write it down yesterday. On the diagonal, the Bergman kernel is the supremum of the ratio between the L infinity norm and the L2 norm. So I shouldn't say L infinity, but really just the value at the point squared. So So that's that, okay? And so if I want to get the formula for the Bergman kernel, actually I don't have to work very hard. I claim it's just extremely simple, given like this. Okay, and so this is really just very similar to how you would prove the Bergman kernel formula for tube domains. Basically, we have these three characterizations, and it has to be holomorphic in the first variable, anti-holomorphic in the second, and it has to be reproducing. And in some sense, this doesn't tell you how you come up with this guess, but once you come up with this guess, you can check these three properties. And so that has to be the Bergman kernel. Okay, so okay, and so now one particular choice of mu, which I mentioned, is the uniform measure. So just you know, uniform measure density has 1 over k. Then actually this is just very similar to tube domains, and the Bergman kernel just becomes e to the L1 support function at the real values of z. Okay, and so this is how the connection to the LP support functions comes about. Okay, and so now now the observation is that, well, Bergman kernels also have associated geometry to them. So this is the standard thing in complex geometry. You can associate a Kähler metric to a Bergman kernel. So you just restrict it to the diagonal, you take log, and then you take essentially the complex Hessian of that, and that gives you a complex metric, if you wish, or a Kähler metric, what's called a Kähler metric. So this is the Bergman metric by definition of associated to that Bergman space. Okay, and then the observation is that the condition that we had before, star B, is nothing but a very explicit inequality on the Ricci curvature. It just says that the Ricci curvature of the Bergman metric is bounded from above by that constant B. So this in Riemannian language just says the Ricci curvature is bounded above by B. Okay, so I won't kind of prove this here because it's really just kind of chasing through definitions, but all the details are in that paper. You can look at that, and now the punchline is that this theorem 3, which says that star n+1 always holds, just follows by adapting an old theorem of Kobayashi, which he wrote it down for different Bergman metrics, but it can be easily adapted here. And the theorem basically says that the Ricci curvature of Bergman metrics is always bounded from above by n+1. So that tells us that star n+1 has to hold. Okay, so that's the complex proof. It's very clean in some sense, but it hides a lot of things, or a lot of theory under the rug, which in some sense is good because you want to attack a very difficult problem, and you want to approach it with some machinery that is sort of extremely well developed and powerful. So I don't know if the theory of Bergman metrics can be that powerful as to solve Bourgain's conjecture, but who knows? So at least it's an approach. So okay. So now, any questions before I? All right. Okay. So I promised the convex proof of theorem 3, and you can sort of judge for yourself what you prefer. I mean, that maybe it's kind of like a personality test. You see which one you like better, and then you can say where you are on the spectrum of convex to complex. So So what's the convex proof? The convex proof is it's basically a lot of linear algebra and integration, and it works like this. So the LP support function actually also it just appears everywhere. It kind of seems like a really useful object. So you can also use it to write the C functional. Okay, and hence also the isotropic constant. So it's just given by this formula here. And this is just an exercise, really not hard, so I won't give the proof. But it's if you know the Hessian of the LP support function at the origin, then you know the isotropic constant. See. Okay, so the idea is we want to estimate this from below. So that means we need to estimate this thing from above. Okay, and so but we have this condition star B, which we can use to our advantage. So the condition star B tells us that something involving the determinant of the Hessian of the LP support function is convex. Okay, and so if that is really nice because I want to bound this thing from above. So if I have something which is convex, I can use various tools to bound things from above. I really just want to bound this from above at the origin. So Jensen type inequality sounds like ideal here. And indeed, that's the case. So the only issue is that there isn't sort of an extremely convenient way to find a measure. Like, so for Jensen's theorem, you need to find a measure. If you want to estimate the quantity at the origin, you need to find a measure whose barycenter is at the origin. And so you need to play with that. Okay. And so that's exactly where LP Santa low points will come in. All right. So we start with this computation. What is the Hessian at any point? Okay, it's just this expression. And so the determinant, you can write it in this kind of block form. So, okay. And now,
Yander, one question. Except for the scaling, the Hessian is the same for all P's. Is that correct?
right. It's just this P comes in here, right? So for a lot of the computations, you might as well just let P to be equal to 1. And that's kind of like the tube domain value. But it turns out that if you really want kind of precise estimates and constants, then all kinds of other P's come in. So here, like 1 over B and 1 over 2B are values of P that come in at the end of the day. So that's why I kind of kept the P going along here. But if you're not so interested in the values of the constants, then you can just let P be to 1. Indeed. All right. So now, right. Okay. So now I want to understand this determinant, and I kind of have to move away from this here. So right. So we do this. So there's a lot of details here. It's kind of a long computation. So I'm just giving really a very sketchy outline, but there is a way to express determinants of this kind of form using an integral over as many dimensions as the size of the matrix, and this is known as Andreev's formula. Okay, and it works for matrices. What do I mean? These kind of matrices which are covariant type or second moment type matrices. So these kind of matrices here, where the ij element is inner product of xi, xj. So, that matrix doesn't look like that initially, but it is if you use projected coordinates. So if you introduce sort of an extra coordinate, and that first coordinate you be 1, then you can think of that as sort of a set of projected coordinates, and then this is exactly the kind of second moments that appears in Andrea's formula. Okay, and so that's what I'm saying here. So our matrix is exactly such a matrix if we use projected coordinates of this form. Okay, and so that formula, and we get an integral type expression for the determinant, and usually in math you try to simplify things. So here I took a nice formula and I complicated it, so it's kind of the other way around. But the reason is that now I'll be able to show it has some convexity property, because just looking at the determinant itself, it's not clear. But if you write it this way, then here you have something positive, and there you'll have something which you can show is convex. So, all right, so that's kind of the motivation, and so now you just kind of write things out, okay? And so we wanted to understand the log determinant of this function. Okay, and so up to some constant, it's just log determinant of this m. And okay, and then we can actually kind of start digging into this formula for m. Oh, okay, you don't see it here, sorry. So into this formula of m. So here I didn't really say what these measures are that I was using here. So these measures have to be chosen to be essentially have densities which are written in terms of e to the minus 1 over p LP support function. So the L 1 over p support function, you use that, and then you get this kind of, this computation works out to the point where you've decomposed the log determinant into some harmless constants plus some multiple of the HP support function plus some remainder term. Okay, and this remainder term now will be convex thanks to this formula. Okay, so this is another kind of computation. So at the end of the day, this thing being this term being convex means, well, you can just put this to the other side, and you've shown that what you want is convex. In other words, star with d equals to n plus 1 holds. Okay, so that's kind of yeah. So that's the convex proof that star n plus 1 holds. All right, so that was theorem 3. Okay, and I still want to say something about theorem 2. So theorem 2 was the fact that Bourgain functional is bounded below by Mahler function, basically. Okay, so maybe I take any questions before I do that. Okay. So all right. So now we go into the theorem 2. Okay, and so so we want to use star B and show that it implies a lower bound on C functional. Okay, so right, so first observation is that there is an easy bound. This, I think, was a question yesterday, right? So the HP converge from below pointwise to HK, just from definition. And so that gives you this kind of estimate on integrals of this form, e to the minus pH1. Okay, so so this will come up in a second. So we will take these kind of densities to do our computations. So right. So now we assume that star B holds. We also know, right? So that means that this thing is convex, and we want to use that to estimate C of k. And C of k, remember, is written in terms of the LP support function as so. Okay, and so what we want to do, as I said before, is we want to apply Jensen's inequality to this function. And to do that, you need to choose a probability measure whose barycenter is at the point you want to estimate, which is 0. So we need something with barycenter at the origin and something that we can estimate. So the measures that we choose are exactly these, okay? And so they are precisely related to the L1 over P support functions. Okay, and so now the useful fact to know is that there is a LP Santalot point. Okay, and so that tells us that we can always translate the body K so that these measures will have barycenter at the origin. So this is the key kind of point, I guess, in this theorem where the LP polarity theory kind of comes in a crucial way. All right. So so now as you can imagine, when you're trying to estimate things which have to do with determinant of Hessians, you need to invoke some facts from Monge-Ampère theory about the Monge-Ampère operator. This is determinant of Hessian is called the Monge-Ampère operator. So and when you do that, and you do various estimates, then the L1 over P and the L1 over 2P Maulich volume come up. And at the end of the day, you get theorem 2 using Monge-Ampère type arguments. So, okay, and so that's kind of the where things are at right now in terms of relating Bergman kernels to Bourgain's conjecture. Okay. So I guess I have just a few more minutes I want to talk. I just want to discuss a few more aspects of LP Mahler theory. So so I mentioned just now, that
Yaner, you have about 30 minutes left. So if you need,
yeah, I know. I mean, I kind of planned this, but then when you give a Zoom talk, it kind of goes faster. So if I use the board, probably it will go slower. But anyway, I'm happy to go into more details if there's more questions. But let me first kind of finish the slide, and then we can see if there's more interest. So also, I once went to a talk, and the speaker said something very wise, is that if you finish 10 minutes early, you make a lot of friends. So maybe this was said by George Varlin, and I think he attributed it to somebody else. So he probably took it from somebody else. So I don't know who is kind of the inventor of that, but I think it's very true. So anyway, so I mentioned the LP Santalot point. The LP Santalot point is really important for the previous theorem. And it kind of almost came by accident, like this LP Santalo point, or this whole kind of idea of LP Mahler, because in some sense, my student and I were working on it from one point of view, and Bernson was working on other things, and then we kind of realized these things converge, and they kind of meet in various interesting intersections. And you really try to do this kind of Jensen inequality in the previous slide, and at first you kind of you realize that for symmetric bodies you can just always do it, because the LP Santalo point for symmetric bodies is always the origin, like in the classical case, and there's nothing really, nothing delicate there. But when the body is not symmetric, there is something delicate going on, because you look at the LP polar body, it's this kind of funny smooth body that's bigger than the polar body. It can be much bigger too, and there's kind of no guarantee that there will be such a point. I mean, so it's when you start thinking about it, you realize it's not completely obvious, and it is indeed not completely obvious, but it's true. So at any rate, once you see that you have an LP Santalo point, you say, well, I should also have an LP Santalo theorem. And that was one of our main results in that paper. And we proved it under a symmetry assumption. So we showed that for symmetric bodies, it's true. And somehow when you're dealing with these LP polar bodies, they're much more complicated than the polar body in some sense, because you have these integral formulas, and it's just kind of a lot of computations just become more technical, not really more difficult in some sense, but just take more work. So that was true, but then we wanted to have this also, like the full Santalo inequality, and indeed Mastraton is I think just posted this paper. So basically you have this inequality for any body as long as you translate it to have the Santalo point at the origin. So no symmetry needed. Okay, so I guess I kind of failed to mention, but I should definitely mention that there's a whole kind of parallel theory of LP centroid bodies due to Luttwak and Zhang and others, which kind of goes back maybe 20, 25 years back. And instead of looking at log of e to the inner product, they just look at integrals of inner product to some power, and then take the corresponding root. And this is kind of a very similar type of quantity on the face of it, but and it has a Santalo inequality, but there seems to be really fundamental differences between these two. For instance, the Mahler volume that's associated to the centroid bodies does not behave like the LP Mahler volumes. So having some sort of Bourgain-Millman theorem for the centroid bodies, it seems to be a much harder thing. So anyway, I don't know the full kind of comparisons, but all I know is that the differences are not cosmetic. There are actually real differences between these two theories. So I think having said that they're different, there's also one place where they're quite similar. Okay, and so this is just a recent result, which is really kind of a learning result for me, I would say, because I don't know all this complexity theory. So, but it's sort of also a reality check. Do these LP Mahler conjectures make any sense? And so the first thing you would want to do is check it holds in dimension 2. Okay, and so we have actually done that. We hope to post this pretty soon. And as a corollary, we get in dimension 2 a conjecture of Dvorsky on tube domains. So he he actually completely independently of all this, I mean, 10 years before, I guess, he conjectured something about Bergman kernels. So tube domains, he conjectured that for the cube, I guess I should normalize this by 4. The cube with volume 1, it minimizes the Bergman kernel among all such symmetric bodies of volume 1. Okay, and as we saw, I mean, this is just the volume of the LP polar, L1 polar. Okay, so this is the corollary of this theorem, which is for NEP. Okay, and in here, the sketch of the proof is really inspired by work in the LP centroid world, where they did also dimension 2. Okay, so this should mention these names. Okay, and so I'm just stating here everything in the symmetric case. That's actually the easier case, and the non-symmetric case is really more complicated, but I won't discuss it. So the symmetric case works as follows. So there's a beautiful idea goes back to Mahler from 85 years ago, in that paper I mentioned yesterday, where he was in a resort, kind of a sanitarium to heal. And so what is the idea? You use the fact that you can approximate any body by a polytope, convex polytope, and you can approximate it in the Hausdorff topology. So in other words, the LP Mahler volume is continuous in the Hausdorff topology. That's something you have to check. But once you check that, then it's enough to just understand polytopes. Okay, and now for polytopes in dimension 2, there is this canonical way called Mahler sliding to take a polytope and reduce the number of vertices. So what you do is you first take the polytope. I didn't draw that step, but you first rotate the polytope so that 2 of the vertices here are on the x-axis, and then there's only one vertex in between them. Okay, and then what you do is you take that vertex and you start sliding it along this line parallel to the x-axis. And when you do that, you do not change the areas. Okay, and of course, since everything is symmetric, you slide in the antipodal vertex in the opposite way. So this is minus q here. And okay, and so when you do that, the area of this middle part, of course, doesn't change. It's not changing. And the area of the triangle is not changing because the height is fixed and the base is fixed. So you can slide in 2 different directions. You can slide to the right or you can slide to the left. And either way, at some point, you will get to a point where now this vertex is part of this line. And so you have eliminated this vertex and also this vertex. Okay, and so now the question is, does the volume of the LP polar body decrease in this process? If it does, that would be great because you have eliminated 2 vertices. You reduce the LP Mahler volume, right? Because the LP Mahler volume is the product of the volume here, doesn't change, and you show that the LP polar volume reduces. And then you just remove 2 more vertices, 2 more, until you get to 4 vertices. And 4 vertices is always affine equivalent to a cube. And the LP Mahler volume is affine invariant, and so you have proved the theorem. So okay, and here
why does the LP the volume of the polar body reduce? and sliding? Is it easy?
Exactly. That's what you want to show. That would be great. Yeah, that's yeah. So so if you can show that, you're done. Okay, so how do you show that? So the point is to show this convexity property, which is exactly what Campi and Gronchi and Meyer-Eisner did. So they did it in the different ways, and we kind of need to use a blend of ideas from their papers and other things too. But what they show is that 1 over the volume, 1 over the in their context, 1 over the classical polar body for them is convex. Here we need to show 1 over the LP polar volume is convex. Okay, if you've shown that, then what you can do is you can, I mean, what that will show is that either the one sliding to the right or the sliding to the left will have smaller Mahler, LP Mahler volume, because this quantity will be convex. So you kind of just, you write this as a linear combination of the quantity here and the quantity. If you put it to the other side, then one of them will be smaller. You don't know which one, but one of them. Okay, so all right, so I guess I should give a little bit more details because the paper is not posted yet. And also I should say that it's kind of scary how long these papers get, even when you prove something in dimension 2. So the paper is like almost 50 pages long, and one of the reasons is that I guess we're novices in convex, so everything we kind of want to make sure is correct, and we write a lot of details. And the other reason is that we want people who are interested in Bergman kernels to understand it, so they don't necessarily have the background. But then the real reason, I mean, I guess that it's a lot of details, just because these LP polars, they're defined in terms of double integrals, and all the computations are kind of become just complicated compared to the classical cases or even the LP centroid cases. And then there's an additional complication for the non-symmetric case. So in the non-symmetric case, that's something that also appears in Meyer-Eisner, but somehow for a different reason. But in the symmetric case, the barycenter is always staying here, and in the non-symmetric case, when you're sliding, you also need to translate and in a certain way, so that kind of complicates things too. So so at any rate, we want this to be convex, and how do you show that? So so in the case of a planar symmetric body, there is a very straightforward formula for the volume of the LP polar. I mean, it's not completely explicit, but it's actually good for us. We need a formula that's not explicit. This is another instance of making something simple complicated in order to use some machinery. So we write the volume so, and then classical kind of tool, Borel, Brascom, Lib, tells you that if you want 1 over this, or if, in other words, if you want this to be -1 convex, then it's enough to show that this thing in the integral here is inconvex. So it's one of these results of the type of some sort of a marginal of something which is convex, has some convexity properties, right? So that's where this kind of family of results comes from. And okay, and so so you want to show this. Now, what is this condition? Okay, here, remember that we have 2 parameters. One is kind of parameterizing the boundary of the body. That's T, and then Q is the parameter for the sliding. So we're looking at kind of norms of a 1 parameter family of bodies. Okay, and so this reduces, okay, and now these bodies, the only difference from sort of the classical papers that I've mentioned earlier is that for us, it's not the classical polar body, it's the LP polar body. So everything has to be done differently. You don't have the homogeneity of the support function and so forth. So instead, we rely on the theorem of Ball to show this type of convexity. Okay, and so that requires a strong joint type convexity statement on the LP support function of this type. Okay, so if you've never seen this before, this looks ugly, but if you look at it long enough, you kind of start to appreciate it. And it's yeah. So I guess that's kind of all I wanted to say. And I guess I did take an hour instead of an hour 15, so maybe I can take questions for 5 minutes and still make a lot of friends.
A question about your LP Sandalo point. Is it affine invariant?
Yes. Yeah. Yeah, everything, like some of these properties really work for any P, like the affine invariance, the tensoriality, convexity of the LP support. A lot of things do carry over, just not the homogeneity.
Yaner, I had a couple of questions. So the first is actually a clarification regarding this bound on the Ricci curvature of the Bergman metric. So you cited Kobayashi's theorem, and I was
Right.
wondering. I mean, initially I thought maybe that I thought the bound was on the holomorphic sectional curvature, but is it that because we are on a tube domain, it ends up being about the Ricci curvature? It is
No, there's various theorems of Kobayashi actually.
okay.
So this one is
Genuinely for the
not
Ricci
like,
curvature.
yeah, this one is not his kind of famous one from the book. This is one from I mean, it's kind of a paper that to be honest, not so many complex geometers know about it, and he writes it for.
Does he do this
Yeah.
on other? I mean, is it only for tube domains, or does he actually get bounds?
No,
for the
no, no. He doesn't do tube domains at all. So he looks at sections of the canonical bundle actually. So and so these are like N0 forms and holomorphic N0 forms, and for those he has some Bergman space, and he has various conditions like some kind of technical conditions that he assumes, but once they hold, he shows the Ricci curvature has that bound, and then you can just adapt it to the setting, and you see that the same proof basically works. So
Okay.
yeah, it's not like exactly off the shelf, but it's pretty close.
Okay. So for a follow-up question, so it seems like the bound in that inequality is important, right? You want to minimize that capital B, right? You said n+1 works, but you would like a better bound.
Yeah, I
So
mean, you would want a bound which is just independent of dimension. That's what you
right.
want.
So that means that that bound is not sharp, or you expect it not to be sharp. So you don't have any tube domains for which that bound is actually attained.
Right. So okay. So that's a great question. So basically, there's a long discussion in our paper about that, and I can summarize it as follows. So there was this flexibility in choosing the measure. So when we choose the measure to be the uniform measure on the body, you get n+1. Or we, the best we could do was n+1, but we hope that you can do better. So so n+1, we don't think it's optimal for that measure, but if you look at all possible measures supported on K, then n+1 is optimal. Like, let's say if you kind of you say what is the best B that would work for all measures supported on K at the same time. Okay, and that is actually n+1, and we give an example. If you take the simplex and you take the measure supported on the vertices, then for that one, all these quantities correspond to the complex projective space and the Fubini-Studi metric. And for that one, the Ricci curvature is exactly equal to n+1. So this n+1 is in some sense, it comes in for a good reason. And it is optimal in kind of a broader sense, but hopefully it's not optimal for the uniform measure. So that's kind of the hope, yeah.
Maybe one final comment, which may not be that relevant to what you're trying to do, but so the Bergman metric, when restricted to these convex slices, would be affine invariant, right? Because affine maps sort of extend to biholomorphisms. But there's also this Riemannian metric known as the affine metric or the Blasty metric, which is also affine invariant on convex sets. And I think there are also some bounds on the Ricci curvature of that due to Calabi. So I wonder if you ever somehow compared Bergman metric to this affine metric in this convex setting. That must also play a role somehow in these problems.
Yeah, that's intriguing. Maybe yeah, I don't know about this actually, but if you don't mind, maybe you can send me some references.
I'll send you
That'd
some.
be great. Yeah.
Sure,
Yeah.
sure, no problem. Okay, all right.
Yeah.
Any other questions? Okay. If not, let's thank Yadir again.
Thank you very much.
Okay. Okay, so can we stop recording?